The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon and good morning. Thank you for attending our first of beginning monthly webinars that we will be conducting in Asia Pacific over the next 6 to 9 months. My name is Charles Cody and I'm the Regional Vice President for Cybereason for Asia. I'd like to thank you for taking the time and attending this and participating with Shlomi Avivi, our Vice President of Information Technology, sharing with you our AI hunting in action. I please encourage you to ask any questions in the drop box on the lower right-hand side. We will be recording this webinar for future purposes if you would like to view it again. And thank you for attending. I'll hand it over to Shlomi.
Hi, everyone. Let me share my presentation. Okay, so let's start. So we are going to, first of all, we're going to talk about AI hunting, and I'm going to present an actual case that that we have been working on. Our team of analysts are constantly helping our customers in threat hunting, proactive threat hunting in their environments, and often we come across cases that that we can present in order to understand how AI hunting is actually done. So without further ado, let's start. So we are going to talk about, first of all, the case framework, meaning what were the opening conditions, what tools we used, and so on. We're going to talk about the attack lifecycle, which is basically the general framework of how we model an attack. And how we address it. We're going to show the threat hunting process that was done using our platform, and we're going to summarize it with some tips for you or for everyone wanting to perform threat hunting. Okay. So we are going to, in terms of the case framework, we're talking about a Cybereason customer that was not a services customer, meaning they were not using our analysts' services ongoingly, and have contacted us when they saw something that they thought would require further analysis, and that's where we came into the picture. The customer did not have only Cybereason deployed. They had a number of security controls deployed on the endpoint, on the network, you know, and you kind of your standard you know, security controls framework, as you can see in many organizations. The important thing, we're going to touch on that towards the end, is that none of their existing tools have spotted anything related to the attack that we found. And one more thing one more important thing to note is that everything that you're going to see, I mean, every part of the actual attack analysis was done using our framework. We did not use any external tools here to detect phases of the attack. We did use, on the side, some tools to analyze files, but basically everything that I'm going to show you can and was done using the Cybereason framework, Cybereason platform. Okay. So let's talk about the attack lifecycle. So the attack lifecycle is a schematic schematic representation of the attack phases. Any attack is every attack is different from one another, but basically you can summarize it and divide it into these phases. Each of these phases can be done differently in various ways, but basically in most cases these are the phases that we see. So let's go over that. So in the end, there is some achievement that the attackers are trying to achieve, some data, some level of control within the attacked organization. So the way that they usually attend to it is they start with external recon, where they're trying to understand the environment of the attacked organization, meaning who are the important people, what are the security controls that are used, what is the technical environment, what operating systems, and so on and so forth. And once they have enough information, they go and try to penetrate the organization. The penetration can be done by luring someone to click on a link or open an infected file, or in many other different ways. Once they are there, they want to establish a foothold, meaning the attacker does not want to rely on someone clicking on a file each time they want to get into the environment. So usually they would create some sort of mechanism that would get their code to run independently. After doing that, they try to understand what is the best path from where they have landed to where they want to get. So let's say that they have assumed control of a person in the marketing department, and they want to get to a data center. So they would try to see what is the best path from here to there. It can go through several other workstations. It can go through the network to some servers, and that can again be done in many different ways. So the place where we have entered this this event was when a user was compromised. So basically the customer had alerted us that they have seen an alert in our system that indicated that the user was compromised, and asked us to look further and see if it's something bigger than that. So let's dive in. So shortly we're going to see the alert screen as they have seen it in their environment. So as you can see, this is a typical alert in the Cybereason platform. You can see on the upper left side, you can see that the title is credential theft, meaning that we have identified a behavior that looked like credential theft. You can see below that there are 8 machines that were affected. and you can see the timeline on the lower side. On the bottom side, you can see the timeline that shows us exactly where it was occurring. I mean, on which machines, in which order, and so on. For us, when we're starting to perform an investigation on that, first thing you would want to see is what are the processes that were involved. So as you can see, there are 2 processes involved. And when we would like to dive into it, okay, then we would see that that the process involved, you can see it shortly on your screen. Yes, so the process involved was called unpack200.exe. Now, when we're talking about, when we're seeing a process that was involved in a malicious operation, first thing we want to see is what can we say about this process, and what type of behavior did the system detect regarding this process. So here you can see that in terms of suspicions, you can see on the bottom side of the screen, we see that we detected it as a Mimikatz suspicion. Mimikatz is a credential theft tool. We can see that it had accessed sensitive objects in the system, and we can also see that there is a certain command line that was used by this tool. Now, so what we did next is try to understand what is unpack200.exe. And so we did a short Google search. And the Google search has shown us that that this is an Oracle Java tool, a tool used for unpacking jar files, which is basically a legitimate type of use. But we know that files can be forged and can be renamed. So what we usually do is we also look at some other parameters of the file. And now the parameters of this file, as you can shortly see, we can see that we can see the file signature, we can see the file classification in several Intel threat intel sources, and while looking at this file, everything seemed pretty legit. I mean, the file was signed. It was signed by Oracle. There were no alerts related to the file, and altogether, it seemed like that this file is real. Now, at this point, we could go either way. A less, let's say, less trained analyst, or someone, or an analyst with less awareness and familiarity with attacks, could easily say that this is a false positive, because we have checked the file. The file is legitimate, is authentic. Then I guess the alert is a false positive. But we had a hunch on this, so so we did continue looking. And now the second thing we looked at on the alert was the command line. And in terms of command line, as you can see, the command line looked familiar, and it looked familiar because it's a Mimikatz command. It's an actual Mimikatz command line. So that's where we got kind of confused, because the file is legitimate, but it does use a Mimikatz command line, which basically, where does that put us? So up until now, this is what we had, and the question that we were asking ourselves was how did the attacker do it? How did the attacker get a legitimate, authentic Oracle file to behave like Mimikatz? So what we did next is we tried to investigate all kinds of directions in order to understand, again, how did that happen? And one of the things that we usually investigate when we see an exe file behaving weirdly is to look at DLLs. Now, for those of you who are a bit less technical, then DLLs are pieces of code compiled by the operating system or by the product vendor, and eventually what DLLs do is they have this compiled code and compiled functions that can be used by exe files later on. So in looking at this exe file, we checked what DLL files it's using. As you can see, we have a list of these, and one of them kind of stands up because, as you can see, most of the files it's using, and this is a partial list, but there were more, most of the files are signed, which basically means that they are authentic, and these are signed by Windows, by Microsoft, and they are also usually located in a certain path in the operating system, where one file is not signed and is located in a different path. It's a C Windows temp/work. So immediately our suspicion went to that one. So we started looking at what we could find on this msvcr100.dll. And so again, from our system, we could get the hash and several details on it. And what we usually do when we want to kind of understand what the world knows about such a file is we check at some intel sources, for example, VirusTotal. And what we saw is that VirusTotal did not really know this file. I mean, it was only submitted to VirusTotal a few days before our investigation, meaning it's a relatively new DLL file, not being used out there by common attack frameworks, and that only one engine from the 66 engines of antiviruses in VirusTotal has detected this as malicious. The rest did not see anything about it. And so from this point, we kind of got the picture, because this file was again was named like a legitimate C++ compiler file, but it was not. Obviously, it wasn't signed, so it's not the original one. And so from our experience, what we understood that happened was something called DLL search order hijacking. Now, what is DLL search order hijacking? So basically, DLL search order hijacking is abusing a certain behavior of the Windows operating system. So as we said before, when an exe file wants to use DLL, a DLL file, it needs to find that DLL file. Usually, when it comes to operating system common DLLs, they're not coming together with the exe, with each and every piece of software, but the software relies on the DLL being there as part of the operating system. So what it does, it looks for it, and there's a certain order by which an exe file would look for a DLL file, and so it starts by looking at the file, looking for the file in the same directory, in the same folder where the exe is. If it can't find it there, it will look for it in commonly used operating system folders. Now, the vulnerability here, or the problem here, is that this whole search process only relies on the DLL name, and it doesn't check anything about the DLL file itself. It doesn't check for any content, it doesn't check for signature, and so if we could place a DLL with the right name higher in the search order, we could get an exe to run the code in this DLL, and we could do that because we know that in the search order, an exe would first look for a DLL in its own folder. So if we could produce a DLL file with malicious code and put it together with an exe in the same folder, we will be sure that the exe would run our malicious code. This is what they've done here. So we did some further analysis on this DLL, and we found out a couple of interesting things. First of all, when reproducing the exact command line, we saw that the output was in fact a Mimikatz output, meaning that someone has taken Mimikatz and compiled its code into a DLL, and did it in a way that when run by an exe file, it would perform the Mimikatz credential theft operation. On the left-hand side of the screen, you can see that there's another interesting piece in the DLL code, and that is a condition. So the attacker who produced the DLL files created a condition that says, if you are called by any file that is not named unpack200.exe, do nothing. And why would they do that? So if you think about it, putting your own malicious code in an operating system DLL file can become noisy, because you don't know who's going to call it. You don't know which operating system software uses it, and eventually what could happen is that something can look abnormal to the user. Some software would stop working. They could see some irregular output on their screen or something, which could get their suspicion and could get this whole operation to be detected by the security personnel at the victim. So what they did is that they wanted to be stealth and to only make sure that that only they could run, they could activate the code in this DLL. So they created this condition. So up until now, we know what was the way that got the attacker to do credential theft, and we know that they got somehow they got one of the users at the customer environment, the attack organization environment, to run this unpack200.exe, and by that run their code. So the next question is, how did they create a persistence method? Because eventually, as we talked at the beginning, they don't want to rely on someone clicking on something each time they want to access the attacked organization. They want their code to run constantly. So we started looking at persistence methods and looking for them in the started looking for them from the alert we had. So if you remember, the alert we had was an unpacked 200.exe during credential theft, but there is another view of it, which is the process tree. So the process tree shows us which process invoked which process. And as we can see here, you can see that unpacked 200.exe was called by cmd.exe, the command line for Windows, and this was called by task eng.exe. And task eng.exe is basically the Windows task scheduler service. And a scheduled tasks in Windows is a great way for attackers to achieve persistence, because scheduled tasks are basically a way to run any code or any executable at a certain time, and in most cases under high privileges. So as we can see here, and you can see on the bottom of the screen, what they did is that they created a task running CMD, which basically is, again, command line interface, and the command line interface ran a batch file called 1.bat that had the unpacked 200.exe command line in it. And so we have now understood what was their persistence method, because if they put it as a scheduled task, they could be sure that that this code would be running at a certain time, and what we assume what happened is that they wanted to harvest user credentials, and they wanted to take them at a certain interval. So each time another user has logged in to the infected machine, the day after they would get their credentials. And just to pause a second and understand what was their bigger plan. So their bigger plan, as it seems so far, is that they wanted to get user credentials in order to move around in the organization, because eventually, if you remember the attack lifecycle phases, they wanted to get somewhere. They wanted to get to some sensitive data. They wanted to get to some sensitive area in the network, to get to some sensitive servers, and eventually, these places are usually not accessible by just any user in the organization. They require high privileges. So assuming that, or understanding that they did a recurring credential theft operation happening all the time and sending it over to them, they were looking for this high privileged user to steal his credentials and to move using that. So the next question was, so if we know what they did and we know how they did it so far, and we understand they were doing credential theft, let's see what are the infected machines, or where are we compromised. And so since we knew that they were using scheduled tasks to run their malicious code, then we just simply, and this is again a built-in ability in our system. So what we did is we were looking for these scheduled tasks, and as you can see, what we have seen is that there were 16 infected machines. Out of these 16, 15 were compromised servers and 1 compromised workstation. By the way, this also gives us another indication regarding the attack, because as we saw in the attack life cycle phases, they landed somewhere and they start moving around and spreading from that place. Now, if we see that there are the majority of infected machines are servers, what we can assume is that they landed somewhere in a server's segment. For example, maybe there was an open web server on the internet that they used and that they could somehow take control of. Maybe there was some application vulnerability that they could use to upload their files and run them on the servers. So that also kind of gives us a direction on where to look for and how to find the penetration method. Now, looking at the numbers of the servers or the names of the servers is good, but we also wanted to understand what was the flow, meaning who is patient 0, or who is their foothold in the network that they were using to get to all these other servers. So looking at the communication scheme between the machines, we could see that there was one specific machine that was communicating to the rest. And to us, what it means is that this machine is probably their foothold, probably the place where they have control and that they can use to expand from. Probably a machine that they have, an ongoing connection to, or the ability to log into wherever they want. And from that machine, they started attacking machines around it. And so what we did next is we wanted to look at this specific machine, because so far, and again doing a bit of recap, so far we know how the operation, how the credential theft was done. We know who was compromised, and we know the order by which the machines were compromised. And so we wanted to look further at this specific foothold machine, and we wanted to understand how does the attacker control the attack, meaning how do they get to that machine, what type of persistence they have on this one, and what is their what we call CNC, or command and control method. So let's look at what we could find on this machine. Okay. So on this machine, we started looking more deeply, and usually when we look more deeply on a machine, we look for general indications, and we look for specific indications. General indications are, for example, processes running that we are not familiar with, any type of unknown services, that kind of stuff. And also, again, since this is a preferred method by attackers, also scheduled tasks. Now, in this case, scheduled task was our preferred place to look for, since we knew that they were using it elsewhere also in the attack. So on this specific machine, what we found out is that they had another scheduled task with a file that we have flagged as malicious. And so looking at it, this time it's not an Oracle file, Java file, but it's a Symantec update file. And again, when digging in, we found out that the executable file was signed and verified, same as we had with unpack200.exe. And again, looking at the modules, we can see that there is another suspicious DLL. This time, what we found out is that they were using what we call a hidden loaded module. Now, what does a hidden loaded module mean? So basically, when loading a DLL, the executable would load the DLL from the disk, right? It's a file, and they would load it from there. What attackers in many cases do is they load the DLL from memory. And what it does is that since it's in memory and not persistent on disk, a security investigator or analyst does not have this DLL file in front of them to understand what it does. So basically, same happened here. We saw that they loaded this DLL. We don't know what it did, but looking at this DLL name, we could see that this is part of a known open source RAT, or remote admin tool. And so what they did is that they used this RAT. They didn't write one on their own, but they used this RAT to get remote administrative access to the server. Now, before moving on, let's think about another interesting point here, because they already had a way to run their malicious code using unpack200.exe. Why would they want to use a different one? And so if you think about it, you think from a security analyst standpoint. So the file that you're seeing the activity related to, if we saw that unpack200.exe was being used for remote connection of some sort, that could be suspicious. What would that be suspicious? Because you don't expect this file to go out on the internet or create any network connections. Here, since we're talking about a file that is used for software updates or signature updates from a security vendor, then even if you saw that it was creating a connection to the internet, you would not immediately suspicious. You would not immediately be suspicious that this is something abnormal, because this file is supposed to go on the internet. Okay, so moving on, we saw that this file was creating a connections to a certain DNS name, and then this DNS name, this hailmh.info, is a DNS record that was created or registered only 5 days before the attack. So what we can understand from that is that they actually created a new server just for this attack. They registered this new address because they didn't want to use any address that was used in an attack before, and that could be flagged as malicious. And this is this was their command and control server. Now, looking further into this machine and looking at this, since we've seen that the files that they were using were located in this path of C Windows temp/work, we looked at what other files are there in this folder. And what we could see is that they had a bunch of executables, some of them with more meaningful names that would look more harmless, and some of them with names that are not not really trying to hide as harmless. And looking at these and the hashes and looking for these hashes online, we found out that this this bunch of executables is part of a recon framework, or a bunch of recon tool repository on the internet. So again, going back to the attack lifecycle, or thinking about what they were trying to do. So they somehow got hold of this server. They have created the scheduled task with a Symantec file performing the command and control activities. And after that, they wanted to again to look around and understand how they can get from this server to wherever they want to get. So they downloaded these recon files. And what do these files do? So they are used for network scanning for specific vulnerabilities or on specific ports, scanning for or enumerating open shares and users using protocols like NetBIOS and others. And basically, they provided the picture to the attackers as to what would be the next best target. So if we look again at the attack lifecycle schema and try to understand where we started and where we are so far, where we ended, is so we can see that we started, as you remember, with a compromised user, and using that lead, which again was not a very strong and indicative lead, something that you could easily mistake for a false positive. Using that lead, we started uncovering and started understanding other parts of the attack. So we started by understanding the persistence and foothold, and then the command and control method, and then the internal recon and lateral movement methods, and the scope of where they got. Now thinking about looking at this attack in a bit more higher view, let's think about what we can say about this attack. So given the type of tools and methods that we've seen, we can definitely again, so there were customized tools and customized files used here. This is not an accidental infection by some common attack. And eventually, we could also see that aside from creating their own custom DLLs used for this attack, they also created a custom infrastructure in the form of servers that they set up, DNS records, and everything around it to facilitate this attack. The attacker were going after user credentials that can be used to move around and to get to the authorized or sensitive areas they set out to get to. And eventually, if you think about it, this is a very powerful method of doing so, because when using an actual a real user credentials, it's really hard to differentiate between this user's legitimate actions and the attacker's actions. We know that there were 16 machines that were compromised, and so we could also scope which are the users that are compromised, because we can understand, we can know who are the users that were logged in to these machines. And so to summarize and kind of understand a more general lesson from this attack. So we can see that targeted attacks, or what we call APTs, advanced persistent threats, are very, very silent and are very aimed for evasion and for not being detected, which means that once an attack is launched on an organization, sometimes there would be very few indications of it, if any. And what we can also say for sure is that traditional security tools, security controls, are not effective in detecting or preventing such attacks. And that is because simply because the traditional tools are based on detecting they are signature based and based on detecting known attack tools. And here what we saw is that, and we see it in APTs usually, is that the tools that were used were custom made and were not known before. The only thing that you could say on this attack, or you could find out on this attack, that is that you could kind of characterize and identify and detect, is the type of behavior. And that's why behavior tools are a key in detecting APTs. Another point I think from the summary is that when getting a lead on something that could look suspicious, it's very important to follow the lead and make the relevant investigative steps before calling it off as a false positive. So three tips that I think we can get from this for you out there building your own abilities in APT detection, and then we'll take some questions. But again, a few tips is, first of all, your analyst needs to be trained on APTs. They need to understand TTPs, the techniques and the protocols. They need to understand the behaviors that can indicate attacks, and they need to be well enough updated in the industry and in new uncovered attacks in order to keep up and being able to detect these behaviors, should they happen on your environment. Again, as I said before, do not disregard alerts as false positive before doing at least an initial investigation, understanding for sure that something is a false positive. And I think the most important tip from here is, do not settle for just a reactive approach. Because here again, the customer could easily say, okay, we saw something that looked for credential theft. We also let's wait and see what other alerts come up, because if no other alerts come up, then maybe the attack did not succeed. But as we could see here, there were no other alerts. If we hadn't taken a proactive approach and started digging ourselves without further alerts being triggered elsewhere, we would not find this attack. So this summarizes it. First of all, as you'll shortly see on the screen, that will be my email address. You are most welcome to contact me or any other representative of Cybereason if you have further questions, or you want to deep dive into any of the subjects that we've seen today. Let's look on some questions. Okay, so first question: does Cybereason has the ability to carve out the fileless malware, the one mentioned in reflected yellow technique? Basically, the answer is yes. We do have fileless detection modules. In this case, since the customer only called us in a couple of days after the initial alert, we did not see enough to get this specific file. But basically, the answer is yes. Okay, how did the threat actor get hold of the credentials in the first place? So again, here we could not uncover the full penetration phase. Again, because we came in a bit late to the attack. We came in only when the customer has raised an inquiry on it. But basically, what we can say is that since we know it was a server environment, our recommendation for the customer is to look at the infected servers and see which of them is open to the internet, which of them is accessible, which of them has vulnerabilities, kind of start looking for application logs on them and try to understand how the penetration part was done. Okay, third question. How does Cybereason work and help in the attack lifecycle incident response process? So and I'll answer it shortly because it's kind of a longer answer and depends on the case. But basically, we do provide incident response services, and we provide managed detection services where our analysts, if you're a Cybereason customer, our analysts can constantly be looking at your environment and performing threat hunting and alerts handling on your environment. And in cases where we do find an actual attack like this one, then we definitely provide incident response services where we work together with the customer to help understand the full attack life cycle, the phases, the tools used, and eventually understand and give recommendations on how to mitigate the attack and how to address the attack root cause. And I think we are out of time, or in 2 minutes we'll have to close. So thank you everyone for being with us today. We hope that you have managed to get as much out of this presentation. And again, feel free to contact us with any question or inquiry you have. Thank you.
Thank you, Shlomi. Thank you for attending, everybody. And we will provide this recording to all of the attendees and people who had registered as well. We look forward to welcoming you on future webinars that we'll be hosting in the coming months. Thank you.